Welcome to the Crazy Hat Chemist, so another video here on solubility. Bam! Today's solubility example number 6. Here we go. If 150 milliliters of 0.0030 molar barium chloride is added to 450 decimal milliliters of 0.0050 molar sodium sulfate, will a precipitate form? So the first thing that we need to do is figure out what the formula for barium chloride is. Barium is a group 2, so it has a 2+ charge. Chloride is a halide ion, that's a 1- charge. The formula for barium chloride is BaCl2. We also need to figure out the formula for sodium sulfate. Sodium is a group 1, it's a 1+ charge, and sulfate is a polyatomic ion, that is SO4 2-. We're going to combine those together and we get Na2SO4. Now, when we mix barium chloride, BaCl2, with sodium sulfate, Na2SO4, both of those are salts, so therefore they dissociate 100%. Now, when they mix together, now the ions of barium ions, chloride ions, sodium ions, and sulfate ions are mixed together. Do any of these ions combine together to form an insoluble precipitate? So what you're doing is you're looking at your solubility rules and you're going to figure out what insoluble precipitate might occur. This is generically a double displacement or a double replacement reaction. That is, barium chloride and sodium sulfate are on the reactant side. The barium is going to combine with the sulfate and the chloride is going to combine with the sodium. So you're going to get sodium chloride, and you're going to ask yourself, is sodium chloride an insoluble precipitate? No, it is not, because group 1s, sodium is one of those, or chlorides, okay, are soluble, except for certain compounds of which none of them are here. Okay, there are no exceptions to sodium. So sodium with any other anion is something in solution. That is, it is not a solid precipitate. Okay, so chlorides, bromides, and iodides are soluble except for barium, strontium, and mercury, lead, and silver. Okay, now barium and sulfate are going to get together. They have the same 1-to-1 ratio, so it's a BaSO4, and that is an insoluble precipitate. So sulfates are soluble except for barium, strontium, lead, and a little bit slightly on the calcium. So that means that barium sulfate is the insoluble precipitate. So what you're going to have to do is look up the value of the KSP for barium sulfate. And that's right here, I've put it right here for you. So the KSP for barium sulfate, that is the proposed insoluble precipitate, is 1.1 times 10 to the negative 10 at 25 degrees Celsius. Again, that's a K value, and those are temperature dependent, therefore the temperature is necessary to include in this. All right, so now what we're going to do is write out kind of what I've given you verbally, okay? All right, now the barium chloride is a salt, like I said before. Salts dissociate 100%. So the barium chloride has a concentration of 0.0030 molar. So what is the concentration of the barium ion? Well, I'm going to look at the barium chloride stoichiometric coefficient of a 1 and the barium ion as stoichiometric coefficient of a 1, and I'm going to use that to get the barium ion concentration of 0.0030 molar. Okay, I'm going to do this just for giggles. We don't really need this information after having told you what we're going to get, and that's the barium sulfate. But I'm going to get the chloride ion concentration so that you know how to do that. So the stoichiometric coefficient in front of the barium chloride is a 1. The stoichiometric coefficient in front of the chloride is a 2. So I'm going to take the barium chloride concentration and multiply that by 2, and I get now the chloride ion concentration, 0.0060 molar. Okay, but I'm really truly only interested in the barium ion concentration, because that's going to form the insoluble precipitate with the anion of sulfate. So sodium sulfate is also a salt. That means salts dissociate 100%. So I've got 2 sodium ions on the product side and 1 sulfate ion on the product side. Okay, the initial concentration of the sodium sulfate is 0.0050 molar. So I'm going to get the sodium ion concentration and the sulfate ion concentration. The sodium ion concentration is 2 times the sodium sulfate concentration, and that will be 0.010 molar. The sodium sulfate concentration is the same as the sodium sulfate concentration, as far as the let me try that again. The sulfate ion concentration is the same as the sodium sulfate concentration because it's the same stoichiometric coefficients of 1 to 1. So the sulfate ion concentration is 0.0050 molar. All right. Now, like I said before, you already know from what I've told you what the insoluble precipitate is, and that's what you're looking at on your solubility rules as you mix these 4 ions together. You're mixing barium ion, chloride ion, sodium ion, and sulfate ion. Okay, so the barium must combine with an anion of sulfate, and the sodium must combine with an anion of chloride. Okay, and you're going to get barium sulfate, which is the insoluble precipitate in this case. Okay, now you notice the equilibrium arrow, it lies predominantly to the left-hand side, that is to the reactant side, as indicated by the KSP value that is less than 1, so this is reactant favored. Okay, you got barium ions and sulfate ions, it's a 1-to-1 ratio, both of them have a 2 plus and a 2 minus charge respectively for barium and sulfate. Okay, so the barium ion concentration is going to come over here. The sulfate ion is going to come over here as well. Okay, what we're going to do is we're going to write the KSP equation for this. That is products over reactants with the stoichiometric coefficients as exponents, recalling that solids are not included in any K expression. So what I get is KSP is equal to barium ion concentration times sulfate ion concentration. The stoichiometric coefficients are 1, so the exponents are 1s here. This is actually the same thing as the Q. This is actually the reaction quotient. So you could replace that KSP with a Q as calling it the reaction quotient. Now what we need to do is figure out what the concentration of the barium and the sulfate ions are together when we mix them together. So we're going to calculate the moles of the barium ion that are present. So we have the molarity and we have the volume of which we have originally of the barium chloride. So we have our 150 mils of barium chloride. We're going to convert from milliliters to liters with that second unit conversion. Then the last unit conversion here is taking the molarity. Okay, canceling our units, we have moles of barium ion, which is 0.00045 moles of barium ion. We're going to do the same thing here for the sulfate ion. We're going to calculate the number of, the moles of ion present, the amount of ion present. Okay, we have 450 mils of this and a different molarity. So that 450 mils, my first unit conversion is going from milliliters to liters, so my units cancel out. Now I'm going to multiply by the molarity, which is moles per liter, and this will yield to 0.0023 moles of sulfate ion. Okay, so these are the moles of barium ion, the moles of sulfate ion that are present when you mix these two solutions together. Now we really are looking for a molarity, okay, and we can't use the original molarity because we are mixing 2 volumes, okay, and they're not the same volume, they are different volumes, okay. So we need to calculate the combined volume. We have 150 mils and we have 450 mils. So we're going to sum those 2 numbers up. We're going to get 600 mils. There's a 600 with the decimal at the end because the ones column is significant for both the 150 and the 450 as indicated by the decimal in both of those. Now what we're going to do is we're going to calculate the concentration of the barium ion and calculate the concentration of the sulfate ion, knowing the moles and the total volume of both the barium and the sulfate. So we're going to divide both the moles of the barium ion by the 0.6 liters and the moles of the sulfate ion by the same 0.6 liters. That is the total volume. This will enable me to calculate the concentration in molarity after the 2 solutions have been mixed. And so the barium ion concentration is 0.00075 molar. The sulfate ion concentration is 0.0038 molar. So where do these values go? Well, this barium ion concentration is going to go right in here for the barium ion concentration. The sulfate ion concentration is going to go right in there for the sulfate ion concentration. Okay, remember, I'm actually crossing out the KSP right here, and I'm actually calculating the Q, which is the reaction quotient. When you do not know if you're at equilibrium or not, you're actually calculating the Q, the reaction quotient. So that's why I call this Q. I put in my two values right here. There's no exponent, so I'm just going to multiply these two values to get my Q, my reaction quotient. So my reaction quotient is 2.9 times 10 to the negative 6. Now, the question really is, will a precipitate form when I mix these two things together? Are there enough barium ions and sulfate ions combined in that new volume to form a precipitate? Okay, so there needs to be enough concentration of barium ions and sulfate ions in order to form that precipitate. So what we need to do is we need to compare the Q, the reaction quotient, to the given KSP value. So that's what we're going to do now. We're going to compare the Q, the reaction quotient, to the KSP. So my Q is 2.9 times 10 to the negative 6. I calculated that. My KSP is a tabled value that you look up, and that is 1.1 times 10 to the negative 10. So from looking at the previous lecture presentation, you know that we're going to compare these values. So are they equal? Is the Q less than the KSP? Is the Q greater than the KSP? So it just so happens that the Q is greater than the KSP. So when the Q is greater than the KSP, that means that it's a supersaturated solution, and that means that it's a precipitate will occur under these given circumstances. Again, if the Q was equal to the KSP, no precipitation. If the Q was less than the KSP, no precipitation. But when the Q surpasses the KSP, it's a supersaturated solution. That means there's more than ample enough ions of that concentration of ions to form a precipitate. That means there's enough barium ions and sulfate ions for them to get together to form an insoluble precipitate, and it will turn cloudy or fall out of solution. Barium sulfate is a white precipitate. Okay, so got that. I am the Crazy Hat Chemist, and of course we can't end without a crazy hat. And of course, you know, everybody's got to celebrate this season at some point in time. Okay, give me a thumbs up if you feel like that video. Subscribe to my YouTube channel. Donate to my YouTube channel. Maybe get a sticker.